Hello students, in this video we will discuss about the second type of circuit topology, which is known as folded cascode op-amp. And before we actually discuss about this folded cascode op-amp circuit topology, let me try to review the drawback that we had in the case of a telescopic op-amp. So in the case of a telescopic op-amp, one of the major problem or the issue that we had faced was that this op-amp cannot be used in a unity gain, cannot be used in a unity gain feedback circuit. So this happens just because the output swing of this unity gain feedback circuit was greatly been reduced within the limit of Vb minus VGS4 plus VTH2, and that is the maximum swing that we can have across the output Vout, and the minimum swing that we can have is written as Vb minus VTH2. Okay, so this is the tight swing that the tight range of swing that we have when we use this telescopic op-amp as an op-amp circuit in a unity gain feedback, right. So now I just want to point out that the value of this Vb can be related to a circuit configuration that we have discussed earlier. That is, when we discussed about an amplifier known as cascode stage amplifier, we had the circuit set up something like this, where we had a load which is a current source load, and followed by this there are two series of transistors stacked one on top of each other, and the transistor M1 is acted as a kind of input device, and the transistor B or the M2 transistor basically acts as a kind of cascode device, and the output is basically tapped across the drain of this M2 transistor. Yeah, so this is the configuration that we had, and in this configuration we found that the value of this Vb is so much constrained. You cannot fix the value of Vb to any desired value. So basically the fixture of this value of Vb is basically constrained by the drain potential or the DC condition at the drain of M2 as well as the DC condition at the drain of M1. Okay, so it is something like it has been stacked between these two regimes where we cannot have a greater swing. Okay, so basically this limitation happens just because the cascode device as well as our input device are having the same similar structure. But later on we found a different configuration which tries to rectify this issue, which is known as folded cascode stage amplifier, or basically amplifier. So in this configuration what we did is that we just try to change one of the nature of this transistor, so which means that uh, if M1 is being built by making use of NMOS device, then M2 has to be built by making use of a PMOS device. So uh, so in a way that we were not having the same similar nature for M1 and M2 to create this kind of amplifiers. So let me try to recall them, because this would act as a kind of base for us to discuss. Let me just try to, yeah. So we had two such cases of folded cascode amplifiers. One we called as folded up, the other one is labeled as folded down cascode amplifier. Yeah. So in the case of a folded up cascode configuration, we had this M1 being realized by making use of a PMOS, whereas M2, which is the cascode device, was realized by making use of an NMOS structure. Similarly, we had a folded down where M1 was realized using an NMOS, whereas M2 was realized using a PMOS structure. Okay, so let me just try to quickly get you the structure that we had, so that we will be utilizing this structure to build the op amp configuration for folded cascode opamp configuration. Okay, yeah. So in the case of this structure, let me just try to bring this structure. What we had was a VDD, and this M1 was realized using a PMOS, where the Vin was applied, and M1 was fixed here, and we had a load, okay, and then followed by this load, we had tapped an output node which is labeled as Vout, and after this, there is supposed to be a cascode device which is being built by making use of an NMOS device and fixed with a voltage of VB. And in order to bias this structure, we had added an extra current source which is known as the tail current source, and this is the structure that we had for what is known as a folded cascode, a folded up cascode configuration. Okay, yeah. So now similarly, one could draw the structure for folded down configuration in a very similar manner, wherein the NMOS device was fixed for the input device, where Vin is applied, and the drain was being connected to the source of the PMOS device, and the PMOS device, which is M2, is being uh, biased with a potential VB, and the drain through which the output is taken, and even the load was being connected. Okay, so here is where we tap the output, and in order to properly bias the circuit, we had added a current source, okay, at the top, and we label this as ISS. Okay. So we have analyzed all these circuit setups in the earlier classes. The only thing right now that I am going to do is that I just want you people to recall, like, how does this change in the configuration of M1 and M2 has really made this VB to change. Okay, so now in this case, one could use a value of VB which is only constrained by this drain of M2. Okay, so you cannot have a value of VB more than the drain potential of M2. Okay, but what happens is that one could freely move the value of VB all the way closer to the value of ground. Okay, and that is what uh, it has happened in the case of a folded cascode amplifier. Similarly, in the case of folded down configuration, the value of VB can rise all the way up to a value which is closer to VDD, but again it has been constrained by the drain potential of the M2 transistor. Okay, so in a way, when you really compare these two structures, here in the case of a cascode amplifier, the VB was constrained by both the drains, but whereas in the case of a folded cascode configuration, the VB was one of the constraint was being removed out of the VB value fixture. Okay, and that is one of the main advantage. But the extra pay that we paid for this configuration is that it leads to an extra current source, or basically this leads to two parallel paths in the circuit configuration, and due to which the power dissipation through the circuit will be higher than compared to the normal cascode configuration. Okay, yeah. So with that, the basic review, let us try to realize the folded cascode op amp. Okay. So now that what I do is that I will just try to utilize the folded up configuration in order to realize the folded cascode op amp with PMOS input or PMOS differential input. Okay, so let me just remove this, and with PMOS differential inputs. Okay, yeah. So let us try to do this particular circuit setup. The only thing that we have to really think is that we have to it's about what is known as a differential output. What we want to create is a differential output, and later we'll just talk about one more configuration where the output is taken as a single ended. Okay, so now let us begin focusing on this particular circuit setup. So in order to focus on this particular circuit setup, I'm just going to utilize the folded up configuration that we had for the simple amplifier structure. Okay, so again there are two such kind of structures that is required to build this differential output. So let me try to grab one of the image, just copy it, and let me just try to paste it. Yeah, and let me also try to create one more. Yeah, yeah, yeah. So there is a few things that I just want to modify here, and let me try to do this modification, and let me try to relabel this transistor M2, or basically try to redraw the structure of M2. Okay, and I add this tail current source towards one side so that the circuit setup would look pretty neat. Yeah. So again at the top we have this tail current. Yeah. So this is something that we had over here, and that has been slightly modified, like circuit wise it is slightly modified in order to look something like this. Okay. So basically it's the same circuit that has been reflected onto this particular part. Now this particular circuit setup has to have a differential input condition as well as a differential output conditions, and due to which I will use a different color to mimic the same similar structure, where I will label this transistor as the M3, and again for differential input let me just try to make it available so that it creates a differential input condition between the gates of M1 and M3. And now I will also try to mimic this similar structure, the load structure, and let me tap this output so that I can have a differential output configuration here, and let me also have our cascode device that has been added along with it, and let us fix this voltage with some sort of DC potential VB, and again this has to be supplied with a tail current which is labeled as ISS1 itself. Okay, yeah. So let me label this one as I1 and this one also as I1. And now we have to connect the drain of M3 to the source of M4. Okay, yeah. So let me just try to connect it here, and this is the circuit setup. It's just the mirror of the M1 M2 ISS I1 configuration that has been reflected on the other side. Okay, but there is something that extra that we need to add here, and the extra that we supposed to add is basically this current source. Okay, so which acts as a kind of source which will help us to remove the common mode variations at the output when there is a change in the common mode input. Okay, so it's the same similar circuit setup that we had when we discussed about a differential amplifier, a simple differential amplifier where we had a tail current source, but here in this case we have a kind of sourcing current source. Okay, yeah. So now let us try to replace each of these current sources with an appropriate set of transistors. Okay, so that the circuit leads to a proper configuration here. Now again I will begin with this ISS. Let me just take a copy of this. Yeah, so one could replace this ISS with a kind of PMOS structure, because that is the only possible way that one could have here. So it's supposed to be a PMOS device, and that has been fixed to some DC potential like VB or VB1. Okay, and let us label it as M naught here. And again, now to replace this ISS once for the NMOS structure. Okay, so these current sources can be replaced with a single NMOS transistors that has been again biased as a kind of current sources with some potential like VB2, and let us label this one as M3, M4, M5 and M6 here. And when I the type of amplifier that is used to realize this I1 and I2 supposed to ensure that they have the same similar impedance that they see when we look down across this Vout node, right. So which means that one cannot use a single transistor to realize this I1 current sources, but rather one has to have a cascode structure in order to realize these current source of I1s. Okay, so let me replace these I1s with a set of PMOS transistors that have been stacked such that they create what is known as a cascode structure. So let me just try to fix the bias voltage somewhere here, which has been connected to the gates. Okay, yeah, and let us label this as MVV3. And similarly, we need a one more structure at the top to be reflected, such that the impedance that we have should balance out the impedance that we have at the bottom of our Vout terminal. So again, we use a PMOS device that has been biased in a saturation regime to reflect the I1 transistors, and let us fix this as VB4. Okay, and let us try to label these transistors of PMOS. So let me label it as M7, M8, M9, and M10. Okay, and this one is connected to a power supply VDD. Yeah, so this configuration is called as a folded cascode opamp with PMOS input differential pair. Okay, and the output is again it's a differential or fully differential uh, opamp configuration. Okay, just because we are having a differential outputs here. And now if one wants to realize a single ended output out of this configuration, then let me just try to copy this structure again and show you how to convert this structure into a single ended folded configuration. Okay, so let me just have some room and let me try to fix. Yeah, yeah. So in this case, the only thing that I have to do here is that I have to remove one of the Vout node, okay, and then try to create what is known as a mirror structure. Okay. So let me first label this one, and we basically have to create a diode connected configuration across this M9 and across this M7 structure. Okay, and yeah, so this is how one could convert a differential output folded cascode op amp into a single ended output folded cascode op amp. Okay, so it is pretty simple. Just by having a diode connected for M7 and M9, one could recreate a mirror structure, a cascode mirror structure over here. Okay, yeah. So now let us try to discuss about the uh, the gain and the output swing of these configurations, and later we'll just try to analyze a problem based on it. Okay, so I'm just trying to take the same structure, which is the PMOS input differential pair folded cascode fully differential op amp. Okay, yeah. So now for this, let us try to analyze the gain. Now the gain of the circuit is pretty simple, just because the circuit is symmetric, right? So if at all, if you try to draw a line of symmetry, the circuit seems to be pretty symmetric around this particular point. So which means that one could analyze this in only half of the circuit to get the differential gain of this particular circuit. And also when the circuit is symmetric, we know that this particular node, which is the common node, can be driven to ground. Okay, so in this case it is this particular node. Let me choose a different color. Yeah, so it is this particular node which we have a VP, and that is basically driven to a ground. So now what is left over is just this configuration where we have the M1 transistor source terminal is connected to the ground, and then M1, M2, M5, M7 and M9. Okay, so using only these set of transistors, one could analyze the differential gain. Now we know that the gain is always expressed as a product of transconductance times the R out. Okay. Now let us try to evaluate this transconductance first. Now the transconductance of this circuit can be analyzed by applying a differential input. So let us label that input to be equal to VID. Okay, I'm not taking VID by 2 here, but rather the entire VID is being applied so that the output can be taken as a complete V out expression. Okay, yeah. So now VID is applied, and also the output has to be shorted towards the ground, so that we try to measure an I out of this expression, right? Yeah. So the current I out, basically when we see here, just because of the value of VGS that we have applied across this M1 is basically equal to VID, it creates a small signal current, and that current is basically defined as GM1 times that of VID, and this current uh, will actually flow through the other way, like in the opposite direction, due to which the current can be defined as something like negative sign of this quantity. Okay, so so here you could able to see that there is a branching point that happens for this current, but when we look carefully, that the impedance that we see across the source of M2 is quite smaller than compared to the impedance when we look through the drain of M5. So the impedance that we have here is basically RO5, but the impedance that we have at the top is basically 1 by GM2. Now, since because the value of 1 by GM2 is quite smaller than compared to the value of RO5, we assume that all of these currents that are coming here is basically being branched across this M2 structure rather than this M5 transistor. Probably I have to use a different color. So all of these currents are basically being driven just because there is a low impedance path, and then it goes and shoots out as an I out current here. Okay, so the I out can be returned as minus GM1 VID, and we know that this ratio of I out by VID will give us the capital GM, and that is equal to the GM1 comma 2. Clear? So now let us analyze the output impedance of this particular structure. So let me try to remove these stuffs. Yeah. So now again, let us look for the impedance that is seen through the drain of M7, and since we know that the M7 is being stacked on top of the drain of M9, we first have to evaluate the drain impedance of M9, which is nothing but RO9. So there is an impedance of RO9 here, and that when we look through the drain of M7, it gets magnified, right? So let me write that impedance as RO9 been magnified by the intrinsic gain of M7, which is GM7 and RO7. Okay, and it's an approximated quantity, and that goes in parallel with the downward impedance. So while calculating the drain impedance of M2, we could see that this M2 is basically stacked on top of the drain of M5. So first of all, we need to evaluate what is the impedance that is seen here before we actually compute the impedance that is seen across the drain of M2, right? So when we try to see here, it is nothing but we have an impedance value which is equal to RO5, but this is not the only single node that has been connected over here, but when we look carefully, it is also the drain of M1 is connected across the source of M2. So one has to take even this impedance under consideration. So one could see that we are looking through the drain of M1, and that impedance value would be equal to RO1. So effectively, the total impedance that we have across the source of M2 is basically this RO5 in parallel with RO1. Okay, so basically what we have is RO1 in parallel with RO5, and that when we look through the drain of M2, it gets magnified by the intrinsic gain of that transistor. Okay, and this is the total output impedance that one could see here. So now there is something that happens when we look carefully into this R out expression. You see, the value of this quantity is quite larger, but whereas when you compare the downward structure, which is composed of NMOS transistors of M2 and M5 along with a PMOS transistor M1, you see the combination of this RO1 and RO5 actually downs the output impedance of it. Okay, so generally what would happen is that this particular downward impedance will be slightly smaller than compared to the value that we attain through this PMOS structure, just because of the parallel combination of RO1 and RO5. Okay, so that is something that we need to give up when we try to have an op amp that can be used for a unity gain feedback circuit. Okay, so it is always something, it's a kind of business where we have to lose something in order to gain something. Okay, so now let us try to do the the analysis of output swing. Now, since because we are talking about a differential output, we always have to have a factor of 2 multiplied by VO max minus VO minimum. Okay, so now let us try to evaluate the expression of VO max here. Now, as we know, like whenever there is an output swing across the common node or across the Q point at the output can go all the way up, provided it has to give enough room for the drain and source of M8 as well as drain and source of M10, and that minimum value that we need to have in order to ensure that these transistors are staying in saturation is nothing but the VOVs, right. So based on this, one could write it as VDD minus the VOV 10 minus the VOV 8. Okay, so again it can be written even in terms of 9 and 7, but it's fine. So when it comes to VO minimum, one could see that whenever there is a negative swing, it has to have enough room for the drain and source of M4 as well as the drain and source of M6, and those values are nothing but the VOAs. But you might wonder, does this lower swing impact the drain and source of this M1 transistor, or basically the M3 transistor? So I would advise you to think on these lines, whether the lower swing would in turn make M3 to move out of saturation or not. Okay, yeah, but in short, it doesn't. It only impacts the drain and source of M6 and M4, and it never impacts the drain and source potential of M3 when we have a lower swing here. Okay, so the minimum voltage swing that one could have across the Vout can be written as VOV4 plus VOV6. Yeah. So with this basics, let us move on to the problem. Let me just copy this problem. Yeah. So here you have been asked to realize just the color, yeah, to realize a folded cascode op amp with NMOS input differential pair. Okay, so whatever we have drawn till now was the same folded cascode op amp, but it was being realized with a PMOS input differential pair. Okay, that's the difference between the question and what we have discussed till now. And also, we are not sure about whether we are being asked about a single ended structure or a differential output structure. But if we look carefully, you could see that there is a kind of specification that is given that the differential output swing is supposed to be equal to 3 volt, which means that you are being asked to design a folded cascode op amp with a differential output. Clear? Yeah. So now again, as I stated earlier, since because the sleeve rate specification is not given in this particular problem or in the specification, one has to rely on the spec, which is known as the power dissipation spec, in order to realize the bias current that is flowing through this circuit structure. Okay, so before that, one has to draw the complete structure of this folded cascode op amp with NMOS input differential pair. So I would advise you people to draw the structure and try to get the answer for this, because there are cases where you obviously will do some mistake, but as of now I'll just copy the circuit which I have earlier, but I want you people to try out by yourself and get the structure. There are a few points that you people have to remember it. Let me try to discuss about those few points on the circuit that has been copied. Yeah. So clearly, this is the structure that was been asked to be realized or to be drawn, and we have this M1 and M2, which is nothing but the input differential pair being realized by making use of NMOS device. Okay, and you see that this NMOS device drains are being connected to the PMOS load. Okay, so this is, let me use a different color. Yeah, so clearly you could see that this is being connected to the outputs through the PMOS structure. Okay, even though the even though the input is an NMOS structure, the drains are being connected to the PMOS upper part, or basically the upper part of the output node. Okay, so please ensure that you keep this in your mind, because because many times I've seen people drawing the structures and connecting them to these points. Okay, so these are wrong. Okay, you cannot have something like this. So either you can remember how the folded structure was being realized and use those concepts when you try to realize this folded cascode opamp configuration. Okay, yeah, this is something that you always have to remember. And once, let us assume that you have drawn this particular circuit. Now let us try to apply the circuit conditions to know the W by L factor for each of these transistors. Okay. Now, as we had discussed before, we have to begin with step number 1 in order to identify the DC bias current condition. So, since because the power dissipation is given, the power dissipation is always is a product of VDD into the bias current, and that is nothing but the I bias, as we had before. It is equal to 3.33 milliamperes. So again, one could split this bias current of 3.33 milliamperes into two different parts. One for fixing the reference current sources for these structures and for these structures, and we dedicate that current to be equal to 0.33 milliamperes, and the remaining part of the current will just, which is 3 milliamperes, will dedicate for this folded cascode structure. Okay, yeah. So hope that you are clear with this, and now we'll just move on to the next step, where we try to fix the value of VOV in order to evaluate the W by L factors. So step number 2 is to find or to calculate the VOVs for the transistors. Yeah. So now again we know that, as we did before, the VOVs for these transistors can be evaluated from the spec, which is given as uh, the differential output swing, right. So from this spec one could directly evaluate it, and let us do the same thing. A differential output is given as 3 volt, and that is equal to twice into the VO max, which is nothing but, here in this case, VDD minus the VOV of 5, and let me use this particular branch of M5 and M3 minus VOV of 3. This is nothing but our VO max minus the minimum point, which is nothing but VOV 7 plus VOV, sorry, it's again a negative sign, VOV 9. So this is our VO minimum condition. So now based on this and based on the value of VD, which is equal to 3 volt, one could quickly realize that it can be written as VOV 5 plus VOV 3 plus VOV 7 plus VOV 9 to be equal to I guess it is 1.5. Okay. Yeah. So now in this case, I guess the output common mode value is not given here. So now let us, like probably in your question, So probably in your question bank, you would find that the common mode output voltage would be given, and based on that you can uh, evaluate, or you can fix the values of VOEs for these structures. But since, because in this case it is not given, let me try to define the VOEs based on the circuit conditions. Okay. Now clearly you could see that the transistor M5 carries most of the currents, right? Because as we had discussed, the current flow across driven by this entire structure starting from M1 all the way to M11, okay, including all the transistors between them, has to have a total current of bias current of 3 milliamperes, which means that each of these branches, okay, this is my branch 1 and branch 2, has to support a current of 1.5 milliamperes, right? And in this 1.5, part of the current has to flow in this output branch, whereas the remaining part of the current has to flow in the input branch. So let us define the current that is being splitted is basically half and half, which means that 0.75 milliamperes of current flows through the bottom structure of the output branch, and the remaining 0.75 milliamperes of current flows through the input branch and again through the M11 transistor. Okay, and this is the current flow that we are trying to fix in these transistors. And right now you could see that the transistor M5 carries most of the current. Okay, so in a way one has to give more importance to that particular current source. Okay, so now based on this, and since because our M5 is basically a PMOS device, will define 0.5 volt for this VOV of M5, just because it carries most of the current. Okay, and right now we are left over with 1 volt. Now this 1 volt has to be split across these VOEs, right? Now the values of VOEs that we would use for these structures is again based on whether we are dedicating more value of VOE for a PMOS or NMOS, right? So since because a PMOS device has a lower mobility than compared to an NMOS device, we would generally tend to give uh, some sort of more VOV value to a PMOS device rather than for an NMOS device. So in such cases, what we do is that we will just dedicate 0.4 volt for this VOE3, and then the remaining 0.6 would be equally split as zero point 0.3 and 0.3 for the VOEs of NMOS structures. Okay, so hope that you're clear with this VOE definition. But right now you might wonder, then if this is the case, how about the VOEs of the input device of M1, M2 and M11? How are we going to define those VOEs? So this is the obvious question that you have to have right now in your mind, just because uh, the design is supposed to support even the W by L factors for input device as well as for the tail current source M11. Now in order to address this VOEs, what we generally do is that let us assume that this particular op-amp is being used in a unity gain feedback as before. Okay, let's assume that there is a unity gain feedback, and let us have our input here, and this is what we have. Now this connection can happen in this structure by shorting this output towards the input, right? So this short is actually making this output to get connected to the one of the input terminal of our op-amp. Okay, and that is basically created by this. Now right now the voltage, so we are being left over with what is the common mode voltage that we have across this, and that common mode voltage is being applied as VGS plus VDS of M11. Okay, so hope that it makes sense. First of all, we need to know what is the common mode voltage that we have. Let us assume that there is a swing, and maybe I have to just pull out a bit more space. Let me just try to, sorry. Yeah. So in this case, we found that there is a common mode voltage which we yet to identify it, and the total output swing away from this common mode voltage supposed to be equal to 0.75, because we have to have a total swing of 1.5 volt, and it goes down all the way from this common mode voltage by a value which is again 0.75. Okay. Now we know that this voltage is supposed to be equal to VDD minus VOVs of M5 as well as M3. So now let us try to evaluate that. It is 3 minus zero point 0.5 minus zero point 0.4 should give us this peak value, right? So that value would be equal to 2.1 volt. Now let us calculate this minimum voltage again. So this is nothing but is the summation of this VOV and this VOV, which is equal to 0.6. So the minimum voltage that we have is basically 0.6. And since because we want to fix the common mode voltage somewhere between these two extremes, we would add up these two values, which is VO max plus VO minimum, and divide that value by half in order to get this mid value. Okay, so which would be equal to 2.7. So that would give us a value which is equal to 1. I guess it is 65. 2.7, maybe. Okay, yeah. So hope that this is the right answer. And now this 1.35 is the common mode output voltage that is available in our design at this particular point, and this common mode voltage is being applied as its input. Okay, through this unity gain feedback, it has been applied over here. So which means that this 1.65, sorry, 1.35 volt has to be splitted as a voltage across gate and source of M2 and the VDS of M11. Okay, and we want this VDS to be the minimum, and that minimum value would be equal to VOE 11, right? So we want to have a split of these values, and let us have maybe around 0.5 volt for this, just because we have dedicated a 0.5 volt for an NMOS device, sorry, for a PMOS device that carries 1.5 milliamperes. Even in this case, this M11 transistor, even though it's an NMOS device, it also carries a current value of 1.5 milliamperes, right? So due to which we'll dedicate a large factor of this 1.35 volt across this VOV, and the remaining value can be used for the evaluation of this VGS2. Okay, so that would be equal to a value which is equal to 0.75, no, 0.85, okay, volt to it. And so right now we have set up all the basic requirements that is required in order to evaluate the WL factors, right? So we'll just move on to the next step, which is step number 3. Which is the calculation of aspect ratio. Okay, so now again, based on the formula that we have discussed before, we know the bias current or the DC current divided by the Kn dash, or basically the mu of either PMOS or NMOS, COX, and the VOV that we have defined in the step number 2. Okay, so based on all these factors, one could evaluate the WL factor for all of these transistors starting from M1 all the way to M11. Okay, so once you compute all these WL factors, the last step is to evaluate the total gain of this particular circuit. Okay, so and now I want you people to evaluate the gain based on this conditions that is being applied onto the circuit. Okay, based on the value of VOV, based on the value of ID that we have defined, I want you people to calculate its gain. And now when you try to compute the gain might tend to be lesser than the value of 2000. Okay, so I would encourage you to use the method that has been discussed in the telescopic opamp problem. Okay, that is nothing but I want you to increase the length and the width of these PMOS device. Okay, that is M3 all the way to M6. I want you to increase the width and the length by a factor of 2 in order to increase the impedance of this particular structure and ensure that the gain that you are getting out of the circuit goes beyond the minimum gain requirement of 2000. Okay, yeah. So with this, let me try to complete this folded cascode op amp, and in the next session, let me talk about uh, the two-stage op amp configuration. Thank you.